So my title is Delta Domes over Equiangular Polygons. And this is a collaboration with quite a number of people. We call it the MIT CompGeom group. And some of you know some of these people, so I'll just read their first names. Hugo, Eric, Adam, Anna, Jason, Freddie, and Joseph Tadlak. Peppa, his nickname is. So it's a group work with 8 people. So let me explain what is a delta dome over a polygon. This is the topic of the talk. So let P be a convex polygon. We'll think of it in the XY plane. And D, the dome, is a convex surface made up of unit equilateral triangles, unit edge length, solely unit equilateral triangles. And the triangles can be coplanar. And we want that when you take the polygon P and the dome, you get a convex polyhedron. And if you intersect the polygon with the dome, you just get the boundary of the polygon. So we want no triangle of the dome to be in the plane of the base. And we want the polyhedron to have positive volume. So this is what we mean by this name. And now I'm going to illustrate it immediately with a rectangle. So take any rectangle here. Is a 4x1 rectangle. This is a 3x2 rectangle. And imagine putting equilateral triangles in a trapezoid here and then here. Then you can close it up and it will make like a roof over the rectangle. Similarly here, the roof is a little different. And here you can see it in 3 dimensions. This is a 3x1 rectangle. And you see you have 4 equilateral triangles here, 4 on the other side, etc. So this is a doming, we call it, of a rectangle. And it's almost obvious that any integral rectangle, in other words, sides of an integer length, can be domed in this way. I'm going to now illustrate a couple other domings before I get into the main part of the talk. So first of all, this is not the only possible doming. So let me go back to here. Let's look at a square, which is, of course, a rectangle. And if you do the roof doming of a square, you get a square pyramid, which I'm holding up here in polydrons, which we used quite a bit in this research, these plastic pushed together. So this is a dome, an obvious dome of a square. And here's another way to dome a square. This is a square antiprism. I also have a model here where the bottom is a square and the top I have left off. It's empty, but you can see that it would be a square. And if I take that square pyramid that I just showed you and put it on top of this, then you have a square at the bottom and a dome made up of equilateral triangles. I'll show you another doming of a square. This one is less obvious. I also have the model here. On the right, you can see the square, which is the red square. And then these equilateral triangles, you see there are 2 green ones on top. And I believe, I didn't calculate this, but I'm pretty sure that they are not coplanar. But we'll come back to this example again. But what I've just showed you is that all rectangles can be domed according to this definition, and that some rectangles, like the square, we already have seen 3 different domings of the square. But I want to warn you, so to speak, that in this talk, I'm not going to investigate at all different ways to dome the same polygon. Rather, the focus will be on, can you dome a polygon with this many edges or this many these angles? And I'm going to use equiangular polygons. And just, can you do it or can you not do it? Not how many different ways. Although that's an interesting question, and we did investigate it, but it's not part of this talk. So this is the main theorem of the work. I'll read it, and then throughout I'll be discussing it. The only 2 parts, A and B. A, the only equiangular convex polygons. So of course, equiangular just means that all the angles are equal. With integral edge lengths that can be domed have n vertices, where n is in this set 3, 4, 5, 6, 8, 10, 12. And that's it. You cannot dome any other equiangular polygon. That's the main result. And for each of these n, B, for each of these n, we can characterize which integral edge length patterns can be domed. So it's not the case, well, with the rectangle, it was the case that any A by B rectangle can be domed. But you'll see later on that this is not the case for all, let's say, octagons. So I will mainly focus on A throughout the talk. Now let me say, where did this idea come from? And the answer is in a question that was posed by a mathematician named Richard Kenyon, 2005, so long time ago. And it was recently answered. Kenyon's question was answered by Dmitry Glazerin and Igor Pak, Alexei Glazerin and Igor Pak, in a paper that they called Domes Over Curves. The question that Kenyon proposed was, can every curve be spanned? And the negative answer is no, which is what Glazerin and Pak proved. So I'm going to explain what they mean by a curve and what they mean by spanned, and contrast it with what we're doing. So we call our process doming. They called theirs spanning. Our P that we're doming is a planar convex polygon, as I mentioned before. Their P is a 3-dimensional, not 2-dimensional, possibly self-intersecting polygonal chain. So it's much broader. Our dome is embedded, which means it's not self-intersecting. And we want them all to be convex. Their domes, or their PL surfaces, piecewise linear surfaces, are in general non-convex, and they're not embedded, but they're rather immersed, which means that they can be self-intersecting. So their work takes off in a rather different direction, and we changed their work, so to speak, into P being a planar convex polygon, the dome being non-self-intersecting and convex. The results that they got, the first one is the negative answer to Kenyon's question, that there is a non-planar unit rhombus that cannot be spanned. And this is a bit of a surprise. This was the main result of their paper, that they proved that you can't always span in their sense. So that was a negative result. The positive result is the next one. It says that every planar regular n-gon can be spanned. So this is planar regular n-gon. So that's very much in our world, in our work here. And they proved they can all be spanned in their sense of spanning, which means non-convex, self-intersecting. So our result is a contrast to this. Here, every planar can be spanned, but we show that only a few can be domed. Okay, so let me first take you through regular polygons to show you examples of doming an equilateral triangle, a square. I already showed you the square, etc. in there. And note that we're skipping 7, 9, 11, and all the odds after, and all the numbers after 13, after 12. So equilateral triangle can be domed by a regular tetrahedron. A square can be domed by a square pyramid or the other examples that I already showed you in the introduction. A pentagon can be domed with 5 equilateral triangles forming a pentagonal pyramid. So those are quite easy. Now 6 is already requires a little bit of thought to dome a hexagon, because if you continue this pattern with 3 equilateral triangles, then 4, then 5, if you do 6 equilateral triangles, of course, it will be completely flat. And that violates the definition of what we mean by doming, because the dome triangles should be above the base, not lying in the base. So how can you dome a hexagon, regular hexagon? Well, this is one way. Use a hexagonal antiprism. So the base is a regular hexagon, and this is called an antiprism in that rather than put the base of the equilateral triangle parallel to here, you do every other one. And that's called an antiprism. And notice here's the top made up of 6 equilateral triangles, and it's flat, and they're all coplanar, but they're above the base. They don't touch the base. So this is a doming of a regular hexagon. You cannot dome a regular heptagon, 7-gon, which we'll come to eventually. How about an octagon? You can dome a regular octagon. One way to see this is to take this shape here, which is known by the long name of a gyro-elongated square diprism, and slice it in the middle, and then you see you get regular octagon. Now notice this pattern, which we'll see later on. Here you have a single equilateral triangle, then you have 3 equilateral triangles here, but the base is just unit length, and then 1, then 3, and then 1, all around. And we'll come back to this example later. So that's 8, 9. Regular 9-gon cannot be domed. Regular decagon can be domed. This is just an icosahedron. Slice it in the middle, and you get a pattern very similar. You get a regular decagon, but again, the triangles, you have 1 triangle here, 3 triangles here, etc. 11-gon, you cannot dome a regular 11-gon. Dodecagon, which is 12-sided. Yes, you can do it. Here is a hexagonal antiprism, which we just saw, but now slice it in the middle, and you get twice as many edges. Rather than 6, you get 12, and this is a dodecagon. It's a regular dodecagon, and that's the last equiangular polygon and regular polygon that you can dome. All the other higher ones you cannot dome. And again, this is in contrast to the Glazern and Bach result. Okay. Now, I mentioned that I showed you 3 different ways to dome a square, just to make the point that there are many ways to do this sometimes. And here's another example. This is a different doming of a pentagon. So I showed you doming a pentagon using a pentagonal pyramid. But here, this is just an icosahedron sliced at the base, and this constitutes a doming of a regular pentagon. And again, there are often many different ways to dome the ones that can be domed, but we're not studying that closely. Everything I've showed you so far is regular, except for the rectangle. So equiangular squares or equiangular foregons are rectangles. Here's an equiangular decagon. Now, this is just an icosahedron, and I've sliced it rather than in the middle, where we got a decagon. I moved the slice up rather than halfway, a quarter of the way. And you get again a decagon, and it's again equiangular. So all the angles at these vertices are the same, but it's not a regular decagon. And notice that here, this edge is of length 1. This edge is of length 3. The next edge, 1, 3, 1, 3, 1, 3. So that pattern continues. I mentioned that we completely characterize those patterns. And this is an example of the type of pattern that is achievable. I think you can see that if I slice even higher, I'll get a different pattern. Now, it may seem, since I've showed you all these pictures where you're slicing one polyhedron to get the dome, you might think that all the domings come from slices, and that's not true, but I'm not going to show that. We have counterexamples to that. Okay, so that is in some sense a long introduction showing you what we mean by doming a convex polygon and showing you examples of regular polygons that can be domed. And now I return to the theorem, part A, that the only equiangular convex polygons with integral side lengths, of course, you have to have integer side lengths because the equilateral triangles all have unit side length. The only ones that can be domed have n vertices, 3, 4, 5, 6, skip 7, 8, skip 9, 10, skip 11, 12. And that's it. And these are impossible. So I'm not going to prove this, but I'll spend the rest of the talk on showing you the steps to proving this. It's actually quite a long proof. The full paper is close to 30 pages. So I'll prove very, very little and ask you to believe the ideas. So I'm going to view the proof of part A in 6 steps. Let me read them quickly, and then I'll go through them one by one. 3 dome triangles per base vertex. This is very important. It turns out to be easy once you see it. This is one of the few things I'll actually prove. This leads to a curvature relation at the base vertices. This is discrete curvature. The non-flat edges are connected. That's a lemma that we need. And these first 3 steps lead to the conclusion that the dome, in order to dome a equiangular polygon, you can have at most 6 dome vertices. And that's an important limitation. You can't have many dome vertices. Then there are 2 other steps that are more geometric, perhaps, and I'll defer discussing those. So now I'm going to run through the first 4 steps. Okay, 3 triangles per base vertex is step 1. Let me read it to you, and then I'll, as I said, this is one of the few proofs you'll see. In a dome over an equiangular n-gon, for n greater than or equal to 7, each base vertex, let's call them B sub I, is incident to 3 dome triangles. This is an example. This was the square antiprism that I showed you. And let's look at this vertex here. So the blue is the base. This vertex is incident to red, yellow, red, 3 equilateral triangles incident to it. That's what I mean. So here, each one has 3. So again, the claim is that if n is at least 7, then you have to have 3 dome triangles incident to each base vertex. And the reasoning is actually not that difficult to understand. So the base angle, let's call it beta, is this expression. And if n is greater than or equal to 7, the base angle is bigger than 120. Of course, if it's a hexagon, it's 6, and it's exactly 120. For 7, it's 128 something, and it gets larger and larger. Okay, so they're all greater than 120. So now imagine that a base vertex is incident to just 1 or 2 triangles. Then it does not give you enough angle. Even with 2 triangles, the most you could get is 120 degrees, 2 times 60. And that's not enough to span an angle beta, which is bigger than 120. So it couldn't attach to it. So it can't be 1 or 2 triangles. It can't be 4 triangles, because then the angle beta plus 4 times 1/3 pi, which is 60 degrees, exceeds 360. And we're not, because we're staying convex, we're not permitted to have any vertex have more than 2 pi incident to it. And of course, 5 triangles would be even worse. So the only way is to have 3 triangles incident. So that's a significant constraint. Okay, so that's step 1. Each base vertex is incident to 3 dome triangles. Step 2, I'm not going to prove, but I will just tell you what it is. Let's let omega sub I be the discrete curvature at a vertex P sub I. So what that means is that it's the total angle gap with respect to 2 pi, 360. In other words, you have various pieces glued in, and you add up the angle and take the difference with respect to 2 pi. That's called the discrete curvature. So that's what we were using in this example here, where we were counting the 3 and the pi over 2 for the square base. So here's the lemma. Let P be a convex n-gon base. In this case, we don't need equiangular, but that's all we're going to talk about in this seminar. If every base vertex is incident to 3 triangles, which we know is necessary when n is greater than or equal to 7, then the sum of the curvatures around the base is 2 pi. This is a little elementary algebra, which I won't go through, but this plays a role that the sum of the curvatures around the base is exactly 2 pi. And where this plays a role, just jumping ahead, is the Gauss-Bonnet theorem, which says that the total curvature over the whole surface must be 4 pi. So 2 pi is used up around the base, which leaves 2 pi for the dome. Step 3 is that the graph of non-flat edges of the dome, excluding the base edges, is connected. Now, why non-flat edges? Because we can have coplanar triangles. We've already seen that in the hexagonal antiprism, where the top is made up of 6 coplanar equilateral triangles. So those are flat edges between the coplanar triangles. And it's important to know the structure of the non-flat edges of the dome. And this lemma says they're connected. That should be pretty intuitive that you would accept this. I'm not going to prove it, but an alternative way to say it maybe is more convincing. The one skeleton of any convex polyhedron, forget what we're doing with the doming, just take any convex polyhedron and the one skeleton, the graph of the edges and vertices, minus the edges of one face, is connected. That should be pretty intuitive. So just imagine taking a convex polyhedron and removing the edges of one face, and you can't disconnect the polyhedron. So that's step 3. And now we finally come to step 4, which is a kind of midway conclusion. So some notation here. Let V3, V4, and V5 be the number of dome vertices that are incident to 3, 4, or 5 triangles. So the dome is made up of vertices and equilateral triangles incident to those vertices, and we're just counting how many have just 3, how many have, etc. So for example, this square prism has one vertex of type of V4 equals 1, because there are 4 incident triangles to the apex, and we're only talking about the dome vertices, not the base vertices. And this is something of a trick that we can take V3, the number of vertices with 3 incident triangles, to be 0, which means that we essentially take them off. If you have 3 equilateral triangles incident to a vertex, you must be forming a regular tetrahedron minus the base. There's no other shape, it's rigid. And if we have a regular tetrahedron, we can just kind of, on the dome, we could just remove it, and still you would have a dome, because you would remove it and leave the base triangle. So that may not be convincing, but let me just assume that this makes some sense to you. So I'm going to set V3 to be 0. Now I'm going to take the lemma that says that the curvatures around the base sum to 2 pi. The Gauss-Bonnet theorem says all the curvatures have to sum to 4 pi. And this leads to the equation that 2 times V4 plus V5 is 6. The 6 this is in units of pi. The 6 comes from 2 times 3, because if you have a V4 vertex, it has 4 equilateral triangles, but it's missing 2. So that's 2/3 pi. And when you clear the thirds, you end up with 6. So this little equation, assuming V3 is 0, must be satisfied. And we get one more equation, and then you'll see where this goes. So the fact that the graph of non-flat edges is connected, means that it has a spanning tree. And if it has a spanning tree, then each base vertex has a non-flat edge incident to it. And these constraints lead to another equation, 2v4, 3v5 plus 2 is greater than or equal to n, where n is the number of vertices around the base. This is not completely obvious, but let me just say that you put these conditions from step 1, 2, and 3 together, and they imply this equation. So now we have two equations in these numbers, v4 and v5, and we're going to solve them simultaneously. And this is a table of the solutions. So let me explain what this is. So this is, remember, v4, forget about v3 because we set it to 0. v4 and v5, number of vertices incident to 4 and 5 triangles. If you try to solve these equations for n equal to 21 or larger, you get no solutions. So that just eliminates those possibilities. For smaller values of n, you do get solutions, and I'll show you a couple of them. So for example, yeah. So look at this. This says there exist solutions where v4 is 1 and v5 is 4. So go back to here. This is degree 4. So this is the 1 v4. And then 1, 2, 3, 4 vertices, and these are degree 5. 1, 2, 3, 4, 5 equilateral triangles on each of those vertices. So this has 1 vertex of v4 and 4 vertices of v5. And that's exactly this line of the solution set. Let me show you also 2, 2. We already saw it. It's this figure on the right where there are 4 vertices on the top, the green here, 1, 2, 3, 4. And this one facing you has degree 5, 1, 2, 3, 4, 5. But these two on the other end, you can't really see them. They only have 4 incident. So there are 2 of those. So 2, 2, v4 and v5 is 2, 2. So back to here. So all of these are possible. But the important thing that we're going to take away from this is not the details I was just showing you, but rather than this means that no dome can have more than 6 vertices. Because this is 6, this is 5, this is 4, this is 3. So this puts a limit on the number of vertices on a dome of an equiangular polygon. So I just showed you those. So here's the conclusion. For an equiangular base polygon for n greater than or equal to 7, there can be at most 6 dome vertices. This is a significant constraint and kind of combinatorial in some sense. And now we're going to move to a more geometric argument, in particular this plus and minus normals, and then the projection of private vertices. And this will complete the steps for the A part of the main theorem. Okay. Now, so we're aiming toward proving that no equiangular polygon for n greater than or 7 can be domed for odd n. So first we want to handle all the odd n, and then we're going to handle the evens will come very easily after the odds. So this would prove, if we get this limit, would prove that 7, 9, 11, and greater than or 13 odd cannot be domed. And then we'll get the same thing for n greater than 14 for all even, and that will then settle that list that I showed you. Now, what I want to show you next, before I go into the details, is the pentagonal antiprism, so that I have a model here. You see it here. You have a pentagon on the base, and you have 3 triangles incident to each base vertex. And here I colored them alternately. And this is not a doming because the top is not equilateral triangles, but you could put a pentagonal pyramid right on top of this, and then this would be a doming. But that's not the point I want to make at this juncture, but rather to get you prepared to understand this issue of the normal vectors. So look at, let's say, this face, where my cursor is, and we can think of it as this red face here. It is, no, I'm sorry. I made a mistake. We have to look at, let's say, this bright yellow face where my cursor is. And the equivalent would be this red face. No, this green face. Sorry, I'm getting confused with the colors. So I'll stick to this picture for a while. This bright yellow triangle, if you look at its normal vector, it's pointing upward above the XY plane with a positive projection to the Z axis. This one points downward. This one points upward, etc. And in fact, back to the polygon model here, you can see that every other one slants in, out, in, out, in, out. And we're going to now use to prove, well, I'm not going to prove, I'm just going to show you the ingredients to prove this in-out relationship for n odd. And then it's different for n even. So here's the claim. If a base vertex, let's call it B2 because we're going to look at B1, B2, B3, 3 consecutive. If you have 3 triangles incident to this base vertex B2. So this would be like you take one vertex here and you take red, green, red. Those are the 3 incident to it. And if the base angle is bigger than 120, which is where we are because we're only working with N7 and larger, then the normal vector N2 to that is upward, and at least one of the other 2 is downward. We'll see that actually both of them are downward, but the proof of the lemma comes that only one or the other. And these normals then will lead to an important constraint. So first I'm going to talk about these normals. And this uses a mechanism called the Gaussian sphere, which many of you have encountered. It's a very beautiful idea called the Gauss map. So over here on the left is a polyhedral vertex and normal vectors. In this case, it's degree 4. So you get 4 normal vectors. And now the Gauss map is you take a unit sphere and you translate these normal vectors whose base is on the center of the sphere. And you get a picture like this. And then you imagine rotating N1 to N2 over this dihedral angle along the edge between them, and the blue arc corresponding to that is the dihedral angle. The length of that blue arc is the dihedral angle. Here it's the dihedral angle between N2 and N3. You see it's longer because the dihedral angle is sharper. So you get a mapping here, and the length of these arcs are the 4 dihedral angles here. And then there's one more constraint which is not easy to see. that's in this picture, you imagine a certain angle alpha at one of the incident vertices. So let's take this V here and think of this angle as alpha. Well, what that maps to at N4, which is between N3 and N1, is the angle here at N4 is pi minus alpha. So back to here, the length of the blue edges is the dihedral angle. The angle in this spherical quadrilateral is pi minus the incident angle here. So there's a beautiful mapping from one world to the other. And we use this and set up the proof. And this just gives you a little hint of how it works. So this vertical normal, which I've labeled N0, is the base. Let's say, again, of something like this, you have the base underneath has a normal vector pointing straight down. And then you can see this light brown equatorial plane, and N2, the middle of the three normals, is above the equator, and N1 and N3 are below the equator, which means that N2 points up, N3, N1 points down. And again, what that means here is the green triangle, its normal vector, let's see, here's a pencil. Its normal vector points up, and the red triangle points down, points down. So this picture is what we want to prove happens, and the proof is by spherical trigonometry, and it's not simple, but it's in some sense elementary. And I'm not going to go through it at all, but rather just claim that we get this lemma, that if a base vertex B2 is incident to three triangles, T1, T2, T3, and if the base angle is at least 120, then the middle N2 vector is up, and the other two, at least one of the other two, is down. Okay. Now let me talk about the dihedral angles. So here's the situation along, let's say this is the base and the base vertices, and I've just drawn it completely flat as an abstract picture. And the plus here means that this points up, and these two point down, and that pattern continues. And what I want you to believe is that when n is odd, let's say for the 5, although we're supposed to be using 7 and higher, but it's harder to do that with the polydrons. So let me stick with 5 for an odd, that all the dihedral angles of the face attached to an edge are all exactly equal. So we go here and ignore the green triangles because they are not sharing an edge with the base, and look at the red triangles, which all do share with the base. And all of those dihedral angles are identical. And in fact, this is rigid, although there's a little flexibility with the polydrons. And if n is even, I don't have a big example, I just have the square here, but that's even, then every other dihedral is equal. So here, look at the red triangles, and notice that if I squeeze this shape like this, you see 2 of these are in and 2 of them are out. So every other one is equal. And the last step here is that if n is odd, you have equal dihedrals, and then the exterior projections include at least one private vertex per edge. What this means is that, I have to go back to, this is for n odd. And we're now looking at these red triangles, which have normal vectors pointing down. So if you look from the top, you're over here, you look from the top, then those red vertices stick out, so to speak. They project outside the base. That's what this picture is supposed to indicate. And because they project outside the base, they are private and they can't be shared by others. And so, whoops. So what this immediately gives you, you see, is if you have n private vertices, but you're only allowed to have 6 dome vertices, then you cannot have 7 or more dome vertices, and that immediately gives you that result. So I just showed you the equal dihedrals. Here's another one where it's very clear every other dihedral angle is equal. Odd, even, going around, tilt out, tilt in, tilt out, tilt in. And so if you have equal dihedral angles, then no equiangular polygon for n greater than 7 can be domed because we have a limit on the number of dome vertices. And if you have every other dihedral angle in no equiangular for even n, then n greater than 14 can not be domed. Sorry, typo there. In both of these, it should be cannot. So that completes what I'm going to show you as proving theorem A. And now for B, I'm just going to give you the very quick idea of the whole picture, the characterization. And this slide is a little bit too dense, but I'll just show you a few things. For example, for n equals 3, there's all the side lengths have to be equal. Of course, that's an equilateral triangle. For n equals 4, all integral rectangles, we saw that already. For n equals 5, they all have to be equal. There's no other way to do it with a pentagon. Let me show you this, which is interesting. For an equiangular hexagon, the side lengths, if you label the 6 side lengths as ABC, A prime, B prime, C prime, then you have to have this relationship, which seems very mysterious until you look at what this looks like. So this is a equiangular hexagon, or a hexagonal polyimond, it's sometimes called. And what this is saying is that C prime plus A plus B has to equal B plus C plus A prime, if you just imagine rotating those out. And so it's an elementary constraint. And for octagons, there's a bit of a constraint. For dodecagons, we already saw this actually, A, B, 1, 3, 1, 3, 1, 3. And when you come to dodecagons, there's a more complicated constraint. But none of these am I going to show you, but rather wrap up now. So we can completely characterize which integral edge length patterns can be domed. So this settles equiangular doming. Open problems. Is there any convex 7-gon that can be domed? Not equiangular, not regular, but just anyone. We found 9 and 11 gons, non-equilateral, but we have not been able to find any 7-gon. Is there any convex n-gon with more than 12 vertices that can be domed? We proved you couldn't have more than 24 vertices, but again, this is not regular or equiangular. This is just any convex n-gon. It may be that 12 is the max, but we've only proved 24 is the max. you can dome an equilateral triangle with a regular tetrahedron, but can any non-equilateral triangle be domed? Anyone. Glaser and Pack conjectured that a 2 by 2 by 1 isosceles triangle cannot be spanned in their terminology. And so since their spanning is a very loose construct, it would also show that they cannot be domed. But this is also unknown. And there are many other open problems. Thank you very much.
Thank you very much, Professor Joseph Orut. So there is a time to the question and answers. So any comments or questions? あ、はい、上原先生。
はい、good morning. こっちは。Good morning, Joe. So, can you show the open problems?
Yes.
Yeah, for example, I'm wondering why this is not solved. I mean, say you have, for example, square prism, a twisted square prism, and put it on a dome, right? It's a dome.
Yes.
So you elongated that one, then can't you get any isosceles triangles?
I'm not sure what you're asking. So you mean specifically for a 7-gon or a 9-gon?
I don't know. I mean, for example, you have a square and a twisted squared prism, right?
Mm-hmm.
And you put some, you put some cap of the 4 squares.
Yes.
And you elongate it to this vertical side. Then can't you get any isosceles triangle?
Okay, I see what you're getting at. I don't have the model here, but if you take, let's say you take something large like a 16-gon, okay,
Mm-hmm.
and you start to do exactly this, where you put 3 triangles in and you build it up, a wall. Then at the next level, it becomes non-convex.
I see.
In other words, you can't just build it up and close it with. So again, I don't have the models here, but it would, like this face is tilted inward, and the face that's joining to it might be tilted outward. So that would rule that out. But
so you mean that it's not convex anymore?
Right.
I see.
We did not explore non-convexity. That's another interesting question, to just remove the convexity constraint and say what can you get without that constraint, but you still want to have embedded non-self-intersecting. I don't know. There's a lot that could be done.
I see. Thank you very much.
You're welcome.
Thank you very much. Very nice talk. I enjoyed very much. And I'm interested in the first question. 7-gons. That is the open problem. And could you give me any sort of idea why the number 7 is difficult? 5 is difficult. Sometimes I can understand, but for the 7, what's the special property it has?
Okay, so many of our lemmas would hold for the 7-gon because they required n to be greater than or equal to 7. So for example, each base vertex would have exactly 3 equilateral triangles incident for a 7-gon. So you should imagine doing what I've done here as like a first layer, but now with a 7-gon base rather than a pentagon base. But then you have to continue it. You can't just put a flat top with, because you can't make a 7-gon with equilateral triangles. So you have to continue going up. And as in the previous question, you have to stay convex. And it just seems that it can't be done, but we don't know why. And as I mentioned here, my hand waving argument makes it seem like you couldn't do 9 or 11 either, but you can. You can get 9 and 11 gons. They're not regular, but we constructed such. So this is quite mysterious to me. There are many constraints, and it's not easy to see how to settle this.
Yeah.
But right now,
Thank you very much. Yeah.
there may be no 7-gon, which would be quite surprising.
So your conjecture is there is no answer. is no.
I better not conjecture, because I have 8 co-authors and I haven't discussed this with them.
Okay. Thank you very much.
You're welcome.
So Joe, may I ask about the 9-gon and 11-gon?
Yes.
Do you have some special property of such a 9-gon or 11-gon? I mean, for example, angles can be, how may I say, non-equilateral, but you have some special property of that positive example, say angles are all the same or something like that.
Yeah. Let me see. Hold on a second while I see if I can get a picture. Yeah. Option. Okay. Let's see. Well, this this is not the picture I wanted to show you, but this shows you, this is a 12-gon, this picture here. And it's like a top view. And you can see the edges are not the same length.
But the angles are the same.
Yes. And no, we don't have that there. No, I don't have a picture of it.
Okay.
But we use something like this where we started with a base on an equilateral lattice, and we're able to, like, here there are 12 edges, 12 green edges. But sometimes you can shrink one of the green edges to be 0 length, and then you end up with an 11-gon that can be done. But it didn't, and that's how we got the 9-gon from shrinking the 10-gon. But we couldn't get a 7-gon by shrinking the 8-gon. That's not very convincing, I know, but it would take me some time to find the right picture. Okay, so there are 2 questions in the chat that I hadn't seen. Thanks for the talk. What can we say about the flexibility of the dome itself, removing the base? Oh, nice question. Of course, if you keep the base in, Cauchy's rigidity theorem says that it's rigid. But could it be? No, so for example, here, this is the square antiprism without, oh, sorry, I'm not getting it in the picture. The square antiprism, but it's missing, well, let's call that the base, the square base, and it's quite flexible. So this has to do with the dihedral angles being alternately equal, so that you get this flexibility. With n odd, you get rigidity. Ah, okay. That's a very good question because we proved separately that for this example where the base is pentagon, and then you use antiprism tiling, so to speak, with equilateral triangles, and then there's empty pentagon at the top. Think of the empty pentagon as the base. This is rigid, even with no base. And we proved that, but the proof is quite complicated, and it was much easier to do it the way that I showed you. But yes, at least the regular odd-gons are rigid without the base. But the even-gons without the base are not rigid. But we don't have a general theorem about non-equiangular polygons. So that's a great question. Oh yeah. In fact, I can imagine that the dome of a regular pentagon grid is rigid, right? And absolutely correct, yes. But as I said, our proof of that is more geometric and a little complicated. And so right now we don't have that proof in the paper.
Thank you very much. So I'd like to ask one simple question. Have you counted the number of possible dome by limiting the number of panels? I know the number is infinite, but I want to simply know how many domes can we make by, for example, 100 panels.
Well, I think, let's see, I think what would happen is the convexity would stop things. In other words, if you were going to use 100 equilateral triangles, then you'd have to build it up and keep it convex. And that's not easy to do. And we were able to prove that 24 is the absolute max that you can have at the base, 24 vertices around the base.
I know.
And even 24, I think, is way too high. I think the answer is 12, not 24. But you cannot have arbitrarily many triangles and retain convexity. I think that convexity is a very strong constraint.
But I think we can scale up while keeping the ratio. So what I want to say, just I want to list up the figure of the dome that we can create with a limited number of panels.
Well, it would be very interesting if you could construct something like that.
Yeah. Anyway, so I'm sorry. Now is the time to close up this section. So thank you very much for nice talk.
You're welcome. It was a pleasure to talk to you all. Great questions. Thank you very much.
ありがとうございます。